Thank you very much for the invitation, Nina, Shin, and Yuwin. Thank you. So indeed, I'll be talking about site percolation on planar graphs and circle packings. I think in this audience, I don't have to say much about site percolation. So let me go briefly over this. So if you have a graph G and you want to perform site percolation with probability P, that just means that you retain each vertex of G with probability P, and otherwise you delete it. Usually one looks then at the connected components of the random graph GP, and this is what we'll do as well. And then the focus is many times, if the graph G is infinite, on the event that there is an infinite connected component, we call these infinite clusters. And there is a critical probability PC such that the probability to see an infinite connected component is 0 if the site percolation has parameter less than PC, and is 1 if it has parameter greater than PC. Classically, percolation is studied on lattices or maybe on regular trees. And if you're in a finite graph context, then on the complete graph. This is the Erdős-Renyi graph. But we will be talking today on general graphs, and the case of general graphs is also of great interest. The focus today is when you take an infinite planar graph, what can be the value of PC? This will be our focus today. Let me also mention all our graphs will be simple and connected, just for the record. And let me mention that besides site percolation, one may also consider bond percolation when you retain edges instead of vertices. But that case will behave differently. So really for us, it's important to do site percolation rather than bond. So this is in all of the talk, all of the percolations are on sites. Okay, so here are some examples, an example on Z squared. Here the sites are retained with probability 0.4, here with 0.59, here with 0.7. And in red, you see the clusters of the bottom and the top, the connected component of them. And you see that percolation starts to happen at 0.59, maybe a bit before. Indeed, the value of PC on Z squared for site percolation, not bond percolation, is 0.59 and a few extra digits. So this is the phase transition for percolation. Okay, and as I said, we will focus on infinite planar graphs. There is a structured graphs, Z, the binary tree, Z squared, T, but there are also unstructured graphs, a general tree, a Voronoi diagram, random triangulations, which I guess in this seminar feature many times. And also what was the motivation for me, the loops of the loop-O-N model, they themselves form an interesting graph. So we will be talking about infinite planar graphs. Okay, and here are some conjectures of Itai Binyamini. The motivating question is how high or low can the value of PC be for planar graphs? Now, this question is a bit maybe not the best formulated, because indeed it can be as high or as low as we want. For a general graph, you always have the lower bound that PC is greater than 1 over the maximal degree minus 1 for the graph. This holds on any graph. You get it very simply. What you need to show is that if P is less than this number, then there isn't any infinite cluster. And indeed, the number of paths of length L that start from a given vertex is at most the degree times the degree minus 1 to the power L minus 2. So the expected number of paths of this that are counted here, that are retained, you have to multiply that by P to the L, and you see that that tends to 0 with L when P is less than this value. So you get the easy general lower bound. This bound is in fact sharp on a regular tree, and you get immediately that PC can be arbitrarily low for planar graphs. And there you can also get planar graphs with PC arbitrarily close to 1, but still less than 1. So the question as written above is not very interesting. However, can we say more for special classes of planar graphs? And Binyamini relates the question to the behavior of simple random walk on G in the following manner. The graph is called recurrent if simple random walk on the graph, starting at some vertex, returns to its starting point infinitely often. Otherwise, G is transient. This characterizes the graph because we think of connected graphs. So it doesn't matter what the starting point is. And so this is the notion of recurrence versus transience. We also would like to talk about the notion of one-endedness. A graph is called one-ended if when you erase a finite set of vertices, then what remains is a unique infinite connected component and maybe some finite components, but there can't be 2 or 3 or more infinite connected components. So for example, Z squared will be one-ended. If you remove finitely many vertices, there's just one infinite component, but Z is not, it will be two-ended. It will be the left and the right infinite component. And finally, a planar graph is called a triangulation if you can draw it in the plane and having all the faces triangles. A triangulation is also edge maximal if you not add an edge without making it non-planar. Yes, Nina?
Sorry.
All right. And then what are these Binyamini conjectures? Well, Binyamini conjectured in 2018 that when you do site percolation at parameter p equal a half exactly on a bounded degree, one-ended triangulation. Bounded degree means all the degrees of all vertices are at most some number that depends on the graph, but doesn't depend on the vertex. Then, if the graph is transient, then at 1/2, the percolation has an infinite connected component. On the other hand, Binyamini asked, is it the case that when the graph is recurrent, then at parameter 1/2, then there is no infinite cluster? So you see that the examples we discussed above, the regular trees are transient, and the PC can be arbitrarily low in regular trees. But what Binyamini says is that on the contrary, because it's transient, PC cannot be arbitrarily high. And in the other direction, if the graph is recurrent, then PC cannot be arbitrarily low. And indeed, 1/2 is a separating threshold. These are the very beautiful conjectures of Itai, conjecture in question. And the focus of this talk is to make progress on these questions. Unfortunately, I do not know how to solve them, but I made some progress and I'd like to tell you about it. You will see in the talk that there is more open questions than answers, unfortunately. Okay, so here is the main result. There exists P naught such that the following holds for all one-ended triangulations. If you have a recurrent triangulation, then at P naught is some fixed number. You may have in mind e to the minus 26, a very small but positive number. Then at this small but positive number, there is no infinite connected component. On the other hand, if the graph is transient and has bounded degree, then at 1 minus this small number, you do have an infinite cluster. So how does this relate to Binyamini's conjecture? Binyamini posed the questions at p equal 1/2. So here we replace 1/2 with a sufficiently small or a sufficiently high but fixed probability. And still this was unknown. So we show that there is a universal lower bound for PC on recurrent one-ended triangulations. And again, the emphasis is that this is universal. In particular, you may try to prove such a lower bound by saying that the maximal degree is not too high and using what we discussed in the previous slide, that you have a lower bound on PC in terms of the maximal degree. However, even though the graph is recurrent, it may have very large, even infinite supremum over the degrees, so that strategy will not work. But still, there is a universal lower bound on PC and universal upper bound when it's transient and bounded degree. And in the recurrent case, you don't even need bounded degree. So this is the main result that I'd like to explain to you. Are there questions about the result? Please feel free to interrupt me at any time and ask questions. Okay. So the main tool that we will use is circle packings. Let me briefly overview this idea. So a circle packing is a collection of closed disks in R squared with disjoint interiors. Let me emphasize that I do not require anything of the closed disks besides being with disjoint interiors. Maybe the disks are, spread out. Here is a disk, and they're not even connected. Maybe there's infinitely many disks. They could have an accumulation point. That is, as you see in this picture, maybe the radii of the disks become smaller and smaller and smaller, and there is a point such that you have infinitely many disks that converge to it. All this is allowed. And then we put a graph structure on the disks. We say that two disks are adjacent if they touch, if they are tangent. For instance, this disk is adjacent to that disk here. So I can put a graph structure like so. In this case, I will get the triangular lattice as the graph. By the way, I didn't mention, but I should have, that the PC of the triangular lattice is exactly 1/2. So the conjecture of Binyamini is tight in that example, the recurrent case. In any case, we will later do site percolation on such circle packing. So that means we erase some circles and retain some circles. We retain them with probability P, and we call the graph after the site percolation PP. And let me also introduce another notion. When you have a triangulation, when the circle packing represents a triangulation, so you see here that it represents a triangulation, the faces of this planar drawing are triangles, you see. So in that case, when it represents a triangulation, then the carrier of it is the union of the disks and the so-called interstitches, which means these little holes between the disks. So you take the disks themselves and the little holes together, and this is the carrier. So in this particular example, you have that the carrier is R squared, all of the plane. And in this particular example, the carrier is the open unit disk, whereas all the boundary points of the unit disks are accumulation points. Accumulation points are very important, by the way. So here it's the entire boundary. And here, just for illustration, I've put a graph which is represented by circle packing. So the graph of the circle packing is this graph. And the very important and famous theorem of Kebe from 1936, later proved as well by Andreev and Thurston, is that every planar graph can be represented by circle packing. Even infinite planar graphs can be represented by circle packing. This will be important in the talk. Okay, so we move on. And how do you know what circle packing represents the planar graph? How do you get a handle on the circle packing that represents it? The following theorem of He and Schramm from 95 is very useful in this context. It is an analog of the so-called uniformization theorem. If you have a one-ended triangulation, then He and Schramm proved G may be represented by circle packing in the entire plane. The carrier is the entire plane. If that's the case, then it's called CP parabolic. Or it may be represented by circle packing in the unit disk, and then it will be called CP hyperbolic, but it cannot be represented by both. So there is a dichotomy for one-ended triangulations. Either their circle packing fills the entire plane, or their circle packing fills the unit disk, but they don't have both things. So they're either this or that. They can be represented by one of them, but not by both. So this is a very interesting dichotomy. In some sense, you can say that the graphs are either big. If they are in the unit disk, then in some sense they're big because they have all these accumulation points. Or maybe you can say they're a bit small. If they're in the plane, then in some sense they're a bit smaller. And indeed, He and Schramm proved that if the graph is recurrent, if the one-ended triangulation is recurrent, then it is CP parabolic. So indeed, recurrence means that it's in some sense a small graph, and then it will be in the plane. And if it is transient and also of bounded degree, then it is CP hyperbolic. So at least in the class of bounded degree one-ended triangulations, being carried by the plane or by the unit disk is the same as being recurrent or transient. This is the theorem of Binyaminishram. And indeed, this will be the tool that we will use to analyze recurrent infinite planar graphs. Recurrent one-ended triangulations can be circle packed in the plane. So our starting point will be the circle packing of the planar graph. This will be how we will analyze the problem. Okay, and then what do we prove about such circle packings? Here is the main result. So there exists P naught, the same P naught as before. You may have in mind e to the minus 26, such that every circle packing, maybe it is in the unit disk, maybe it is in the whole plane, maybe it has many accumulation points, maybe it doesn't have, maybe it doesn't fill neither the disk nor the plane, any circle packing. If you perform site percolation on it with probability P naught, then there is no infinite cluster of infinite Euclidean diameter. What I'm saying here, I'm not ruling out infinite connected components. Maybe it has infinite connected components, but all of these infinite connected components are infinite in the sense that they go to an accumulation point. So for instance, maybe the circle packing represents a binary tree or some other tree. Maybe the circle packing looks like this picture over here, this one. When you perform site percolation, maybe you will have an infinite path that's retained in this picture, but this infinite path will go to an accumulation point. In this case, a point somewhere here. What I'm saying is that there cannot be, when you perform site percolation with parameter P naught, an infinite cluster that goes to infinity, the Euclidean infinity. Of course, it is very important that we look here at the circle packing. So somehow infinity is distinguished from the finite accumulation points, for instance, by the result of Binyaminishram. Binyaminishram say that circle packings in the unit disk cannot also be circle packings in the plane. Somehow infinity is special. So the theorem also gives infinity this special position. You cannot have an infinite cluster going to infinity. And here is a quantitative refinement of the previous statement, not quite a refinement, but related statements. If all the circles in your circle packing have bounded diameter, the largest possible diameter is D, then when you start at some disk C naught, and you wish to connect to distance r after the percolation, so you wish to go from C naught to distance r by means of retained disks, then the chance of that happening is exponentially small in r over d. This is the main result, and I would like to explain the proof of this result to you. So this comment I already said, you may go to accumulation points, but not to infinity. And this connects back to the problem, to the previous main result that I stated, that if you have a one-ended triangulation which is recurrent, then it has no infinite cluster. And the reason is that indeed, if you have a one-ended recurrent triangulation, you may represent it by circle packing in the whole plane via the Binyaminishram theorem that we discussed. It will have no accumulation points. So if you have, any infinite connected component must go to infinity because there are no accumulation points. So in fact, the first clause of this theorem shows that there is no infinite connected component. And that means that also on the original graph, before you circle packed it, there was no infinite connected component at parameter P naught. So in fact, the result that is stated here, combined with the Binyaminishram theorem, proves the result that was stated over here, proves the first clause of it. Regarding the second clause, you need a bit of an extra argument. I will not explain it, but it is not difficult. And it uses, for the second clause, you need this quantitative refinement over here. Okay. So in the remaining time, in most of the remaining time, I would like to explain to you how this theorem is proved. Again, are there questions about that before I start? Okay, if not, let me just indicate something about the basic strategy. I didn't prepare a slide on that, but let me just give you some idea. Usually, when one wants to prove that there is no percolation at a small parameter, what one may do is to enumerate all of the paths of length L. Here we start at some C naught, so all of the paths that start at C naught and have length L, and say, well, the number of such paths grows exponentially in L with some rate of the exponential. So if I take P sufficiently small, then it will there will not be any open path. The problem is that I want to take P not universal, and there exist circle packings for which the number of such paths grows faster and faster. For instance, let me draw square packings. Very soon I will talk about square packings because it's more convenient to draw, and technically it's slightly easier to prove, but it's the same idea. So let me draw squares. For instance, consider a square packing that has this structure. It looks more or less like Z squared. So you see squares that look like Z squared. But between these Z squared, I put very small additional squares like that. Very small guys like this. Now I can put as many, by making the squares in the middle small, I can put as many of them as I'd like. And therefore I can make the degree of this graph, and in particular also the number of paths that start at this point, as large as I want. If I want the number of paths of length L to grow like 1,000 to the L, I'll just put 1,000 little squares between these two guys, and I can make the number of paths grow very fast. So this will be an obstruction to the proof. But what is obvious in this example is that if the big squares don't percolate, if I just think of the big squares as Z squared, and if they don't percolate, then also with the small squares, it will not percolate. So really what's important is only what happens to the big squares, and the small squares can be ignored. And indeed, the strategy of the proof is to do some kind of union bound over all paths, but we don't really consider all the paths because there are too many. Instead, we make reduced paths out of path by keeping only the large squares. You will see something like this in the proof. I can say more like at the end if the people are interested about the strategy. Okay. Right, and lastly, before I go to the proof, let me just say that I conjecture that in fact, in this theorem, you don't have to take P naught so small. I conjecture that you may actually take it to be 1/2 in this non-quantitative part. And if that was the case, I don't know how to prove it. If that was the case, it will give a positive answer to Binyaminishram's question on recurrent triangulations. That is not just at P naught, but actually at 1/2, like Binyaminishram asked. Okay, so let me now go to the proof. So as I said, it will be technically convenient to work with square packings. The proof for circle packings is very similar, but it's nicer to draw the squares and also technically easier at one step. So I will do things with square packings, but it's more or less the same proof. I will indicate also afterwards that there is a much greater extension for which the proof works. So a square packing is a collection of squares, closed squares. And again, squares are adjacent if they intersect. And again, we do percolation by retaining each square with a small probability P independently, and we will take P to be e to the minus 26. Okay, so I will work with the L infinity distance, it's convenient. So this event will come up in the proof a lot. This is the event that you start from a square having diameter at most d, and you have an open path from it using only squares with diameter at most d. So all the retained squares on this path have small diameter, and you reach distance r, Euclidean distance r, not the graph distance, the Euclidean distance r. Okay, using only squares of diameter at most d. This is the event whose probability I would like to bound. It is closely related to the event that was indicated here, the chance that the disk is connected to distance r after percolation when all the diameters are at most some capital D. So what I will actually prove to you is the following result. Suppose you have a square packing. I will assume that all the squares have diameter at least 1. This assumption is easy to get rid of, but let me not get into the details. Then the chance that a square connects to distance r using only squares of diameter at most 2 to the k, that chance is at most e to the minus r over 2 to the k. This statement is very similar to the quantitative statement on the previous slide, and this is what I'd like to prove to you. Okay, this for any r, any k, any starting point, any starting square S0, and I also assume that the starting square itself has diameter at most 2 to the k. We will prove this statement by induction, and the next slide discusses the induction hypothesis. So, okay, here I just repeated what we need to prove, the same as the previous slide. We will do a double induction on k and r. The base case k equals 0. So this means, because I assumed that the squares have diameter at least 1, this means that they also have diameter at most 1. So actually, all the squares have diameter exactly 1. So that's a very easy case. In that case, the worst that can happen is that you look like a square grid, so that S0 has at most 8 neighbors. Any square has at most 8 neighbors. So here you can use this counting argument. The number of pads in this graph is at most, of length L, is at most 8 to the L minus 1. And the expected number which are retained after percolation, that's multiplied by P to the L. So if P is less than 1/8 e to the minus 1, then the probability is at most e to the minus r to retain 1, and you obtain the induction hypothesis. So this was an easy base case. This was the base case about k. I will also describe a base case about r, also very easy. But here is the first induction hypothesis. I will assume that we know the result for k minus 1, because I've done it here for k equals 0, and k is greater or equal to 1 now. So this is the induction hypothesis. Another base case is when r is small. If r is at most, say, 2 to the k plus 1, then what's written here is that the probability to connect should be at most e to the minus 2. And here I use a very simple trick. The chance that you're connected to distance r, well, that's at most the chance that the initial square S0 is retained. That also has a chance. That also has a chance p, no matter how it later connects. So if you take p to be less than e to the minus 2, then you satisfy the induction hypothesis. So you satisfy, sorry, this the case r less than or equal to 2 to the k plus 1. So this allows me to make a second induction hypothesis that I assume r is greater than 2 to the k minus k plus 1, but I assume that we know the result up to r minus 2 to the k. So this is the double induction. There will be one extra preparatory step before I go into the actual proof, so to speak. The next preparatory step, I would like to use all these induction hypotheses. In particular, I would like to use the fact that the result is known for k minus 1, but I cannot do it directly because all I know about S0 is that its diameter is at most 2 to the k. And in order to use the induction hypothesis for k minus 1, S0 will need to have diameter at most 2 to the k minus 1, a little bit less. So the next slide is concerned with that. Diameter of S0. So in order to obtain that the diameter of S0 is at most 2 to the k minus 1, if this was not already the case, we will cut S0 into 4 squares. This is the place where it's technically convenient to use squares rather than circles. This is a technical point. Again, I will show you a much greater generality afterwards where the argument can be used. So you cut it in 4, and then you consider 4 times the basic problem. First, you take this square, and you forget the other ones, you remove them, and you ask whether, when you take that square and remove the others, whether there is percolation to distance r starting from this square. If not, you ask whether there is percolation to distance r starting from that square or that square or that square. So you do the percolation 4 times, and the aim is to prove that for any of these 4 percolations, the chance to go to distance r is at most 1/4 e to the minus r over 2 to the k. So because you have only 4 of them, that would mean, via a simple coupling with the original process, that the chance for the original process to go to distance r is at most e to the minus r over 2 to the k, like what we wanted to prove. So this is a rather technical point, but it allows me to assume that the diameter is at most 2 to the k minus 1 by paying only the extra 1/4 factor. So if I will prove a sharper result, then I can make this assumption. And this is what I will do. So now starts, in a sense, the actual proof. So let us recap. You have a square packing whose squares have diameter at least 1, and you have some k at least 1. You need to prove that for any r and any s0, any starting square, and now I make the assumption that its diameter is at most 2 to the k minus 1, a little smaller, the chance to be connected to distance 2 to the k, to distance r by squares of diameter at most 2 to the k, is at most 1/4 e to the minus r over 2 to the k. This is what we need to prove. And what we assume by induction is that the same bound holds without the 1/4 for k minus 1 and all r, and also for r minus 2 to the k. So this is what we will do. And here is the basic idea of the proof. In order to go from S0 to distance r, you have to do one of 2 things. Either you go to distance r using squares of diameter at most 2 to the k minus 1. You never use, you're allowed to use squares of diameter up to 2 to the k, but in fact you don't use them. You only use up to diameter 2 to the k minus 1. That's one possibility. Or you do use somebody of diameter between 2 to the k minus 1 and 2 to the k. Let's call this somebody s. So what happens is that you go up to a neighbor of s with squares of diameter at most 2 to the k minus 1. And then from s, starting from s to the end, you go with diameter at most 2 to the k. And certainly one of these 2 things have to happen for some s, and you have to go over all possibilities for s, if the original event is to happen. So we will bound the probability of each of these 2 possibilities. Let us start with this easy case, when you go to the distance r with using only diameter 2 to the k minus 1. In this easy case, what do you have? So the chance to go to distance r with 2 to the k minus 1 by the induction that holds up to k minus 1, is at most e to the minus r over 2 to the k minus 1. I need to compare it with e to the minus r over 2 to the k. So actually it is e to the minus r over 2 to the k times a small factor. Small factor because I've assumed r is greater than 2 to the k plus 1. So it gives me a prefactor e to the minus 2, which is smaller than 1/4. So I'm still fine. So I've bounded the probability of the first event. And what remains to be done is to bound the probability of the second event. And this is what we will do now on the next slide. Okay, so I need to bound the chance to go from S0 to a neighbor of S, and from S to distance R, the first path using only squares of diameter at most 2 to the k minus 1, and the second squares of diameter at most 2 to the k. And I will need to go over all possibilities for S. So let us see this here. There exists S, its distance is at most R, its diameter is between 2 to the k minus 1, 2 to the k. You connect to a neighbor of S with diameter at most 2 to the k minus 1. You connect from S to distance R from the initial square with diameter at most 2 to the k, and these connections use a disjoint set of squares. What is the probability of this event for a fixed S? Well, you may use the BK inequality because the connections use a disjoint set of squares. And okay, so if you use the BK inequality, you get the Vandenberg-Kesten inequality for percolation. You get that this probability is at most the product of these two probabilities, the probability to go from S naught to the neighbor of S, and the probability to go from S to distance R. So this is what's indicated here. S naught needs to go to this distance from it, and S needs to go to this distance from it. Actually, it might need to go further. So I've written here a lower bound on how far it needs to go. And these two events are what I know how to bound using the induction hypothesis. So I use the induction hypothesis. What does it give me? For the first event, to go to this distance, using diameter at most that, I get e to the minus this distance, divided by 2 to the k minus 1, divided by the maximal diameter. I can use this bound, but sometimes it is better for me if the distance of S naught and S is small, then I may get a better bound if I just say, no, I'll just use something simple. I'll just say that S naught itself needs to be retained. And that has probability P. So if I just discuss S naught, forgetting about all the rest of the blue path, then I get probability P. And I can decide which of these two bounds I use, so I get the minimum of them. And for the second event, I'm going to use the bound that is given by the induction. S is much closer. It needs to go to a distance smaller than R minus 2 to the k. So I can use the induction on R. I know that the claim holds when I have to go to distance less than R minus 2 to the k. So I get e to the minus this distance divided by 2 to the k. Okay, so this is the bound that I get out of the induction hypothesis. And I may write this bound a bit more simply, and this is what's done here. Notice I want to compare everything to e to the minus R over 2 to the k. This factor appears here. So I take this factor out and I put it here. And here there is a 2 to the k divided by 2 to the k, that's a plus 1. And this one is d s naught s. So I get this bound with the p. And what is interesting to notice is that if I instead use this part of the minimum, because the distance of S naught to S is divided by 2 to the k minus 1 here, and by 2 to the k here, then actually this is larger than that. So actually the distance of S naught and S works to my advantage. And this is very intuitive. The further I need to go using only squares of diameter 2 to the k minus 1, the better, because it's harder to go far with such small squares. So I will get a better bound if I need to go very far. And this is why this bound depends on this distance in a way which is beneficial to us. So the only thing which remains is I have to go over all possibilities for S. I just did the calculation for a fixed S. So now I will go over all possibilities. And this is the next slide. So we obtained the following bound, and I have the sum over all S, which have distance at most R in diameter between 2 to the k minus 1 and 2 to the k, like so. And for the last part, I use area considerations. How many squares S can there be that have distance m times 2 to the k from S naught? So here is S naught, and this is a larger region of size of distance m 2 to the k, m 2 to the k. How many big squares can there be in this region? The diameter of such squares is at least 2 to the k minus 1. So here is one of them, here is another, and they all have to have disjoint interior. So by area considerations, there can be at most m squared of them because we are in dimension 2. So only a polynomial number, actually I don't care about the power. And so the number grows polynomially, but the benefit in the probability to me is exponential in the distance. When you divide by 2 to the k, you get e to the minus m. So it's easy to sum this, to make this summation and observe that only the squares s which are close to s naught make a significant contribution. For these squares, I can take p very, very small. And in this way, I can make what is in the parenthesis less than a quarter. When it's less than a quarter, this is what I wanted to show. So it finishes the proof by induction. This was the end of the proof. I hope it was possible to follow. So we have proved the inductive statement. It is more or less what we wanted to prove. I will not say more about that. And I'll just remark that these earlier considerations that we used over here, those are the only place in the argument where the fact that we have squares instead of, say, rectangles is important. So we could have tried the same proof for the original infinite planar graph, but it wouldn't have worked because we don't have these earlier considerations. It was important to circle pack or square pack the original graph in order to have these earlier considerations so that we may identify the big squares and the small squares. I would be happy if I knew on the original graph who is mapped to the big square and who is mapped to a small square so that I may run the proof on the original graph. But this information is, I don't know how to work with it, how to obtain it. But this was the reason we did the circle packing. Okay, in the remaining time, let me present some extensions and many, many additional questions and conjectures. So this is the extension I was alluding to previously, that the proof is really not for circle packings. The proof I just explained for square packings is not for circle packing, is not for square packings. You may do this proof in much larger generality. Here is a generality that I hope to put in a revision of the paper. It is not yet there, but it follows from the same methods, slightly tweaked. So take a metric space and take a countable collection of subsets of X. These are like the circles or the squares. Each of them has finite diameters, but we don't assume that they are a packing. So it is possible that these shapes overlap. So you may consider, for instance, circles in the plane, which may overlap, for instance. And let us say that two of these sets are adjacent if they indeed overlap, if they have non-empty intersection. I will put some restriction. Instead of saying that they are a packing, I have the following condition. For any shape in my collection, the number of other shapes whose distance is at most rho and whose diameter is at least t is bounded by this. Basically, the ratio of rho and t, or the diameter of S and t, is bounded by something. Then there exists a probability depending only on these two constants, C1 and C2, and not on the particular collection or particular metric space, such that there is no connected component of infinite diameter after side percolation with parameter p. This is more general than what I explained to you earlier, because, for instance, if you take a packing, an actual packing of shapes in a Euclidean space whose volume is proportional to the n power of their diameter with a uniform proportionality constant, then they satisfy the assumption and hence the conclusion. So this is more general than the square packing or the circle packing I told you about. And it also highlights, in fact, that the result is not really about planar objects. The only reason that I told you about planar graphs is because of the circle packing theorem, which doesn't have an analog in higher dimensions. But once you have a nice representation of your graph, a representation satisfying this condition, then you can run the proof. It is not a planar proof. Okay, another extension. Instead of working with recurrent planar graphs, you can instead work with Binyaminishram limits of finite planar graphs. I tell this only for those that know what is a Binyaminishram limit. it turns out Binyaminishram proved, and you have to extend it slightly, that any Binyaminishram limit of finite planar graphs has a circle packing with at most one accumulation point, may be represented by a circle packing with at most one accumulation point, and hence you may use the same proof about the circle packing. Actually, this was the motivation. So this shows that on any Binyaminishram limit, there is no infinite cluster in GP for P, which is e to the minus 26, for all of the Binyaminishram limit. That's a large class of graphs. This was actually the motivation for my study of this, this problem, because I needed that last result for the study of the Lupoen model. If there is interest at the end, I have some slides on the Lupoen model to explain this idea better. Finally, we used the one-ended and triangulation assumption. So just go back briefly to the main result. Sorry for that. The main result was that if you have a one-ended triangulation which is recurrent, then it doesn't have an infinite cluster at P naught, and if it's a transient and bounded degree, then it does have an infinite cluster. The first clause, this clause, probably doesn't need the one-ended and triangulation assumption. It still needs to be recurrent, but probably doesn't need to be one-ended in triangulation. At least in the bounded degree case, I have some idea in progress for this that I haven't yet checked in full. The transient case does need it to be a triangulation. If it's not a triangulation, then you cannot connect. In order to create an infinite cluster, things have to connect together. If it's not a triangulation, things, circles don't connect. Maybe your graph is just a line, then nothing will go to infinity. So, but if you assume it's a triangulation, maybe you can do away with the one-ended assumption, maybe. Okay, so this was the final extension that there is some idea in progress to extend to non-triangulations. And if that is done, then it replaces the Heshram theorem with the theorem of Gurel-Gurevich and Nachmias and Shuto. Okay. Finally, many open questions. Since I'm running out of time, I'll go a bit briefly over this, but we may discuss further. First, I conjecture that if you take any circle packing, then you may replace the P naught in my theorem by 1/2. That means that if you do side percolation with chance 1/2, there will not be any infinite cluster that goes to infinity. Maybe it goes to an accumulation point, but not to infinity. If that is proven, this is a very interesting question, then it will imply a positive answer to Binyamini's question on recurrent one-ended triangulation. Similarly, for each P which is slightly smaller than 1/2, I conjecture that if you have a circle packing with bounded diameters, then the chance that a given disk is in a cluster of diameter at least R decays exponentially fast in R over D. So not only do I conjecture that there is no infinite cluster at 1/2, but for any P smaller than 1/2, you should get exponential decay of connection probabilities if you have bounded diameter, and the rate of exponential decay does not depend on the particular circle packing. It is some universal rate, f of p. So this is also conjectured. If this is proved, then it will almost prove Binyamini's conjecture on transient bounded one-ended triangulation. It will show it for any p greater than 1/2, that for any p greater than 1/2, there is an infinite cluster. Binyamini conjectured that at p equal 1/2, there is an infinite cluster. That would be stronger. Okay, and I'm also interested in studying this not only for circles, but say for ellipse packings. So I will imagine that similar things happen for ellipses when you also depend on the maximal aspect ratio of the ellipses. And it is interesting to me to study that case because it was motivated by Lupoen model, but let me not go into that. So to understand something about non-circles, I would say, beyond what we know at the moment. Okay, and finally, the critical case. So suppose you have a circle packing that represents triangulation carried by R and has bounded all the circles of bounded diameter, or maybe maybe you may assume that the diameter of circles grows as you go away from the origin, but let us assume it grows sublinearly. If it grows sublinearly, then you may use the previous conjecture, and supposing that these two conjectures are correct, then it will imply that for any triangulation with carrier R and satisfying these diameter restrictions, PC is exactly 1/2. So again, we know that PC is exactly 1/2 for the triangular lattice. That's one example. This is telling us that if you have any triangulation with carrier R squared and some restriction on the diameters, then PC equal 1/2. It's a very broad class of graphs that have PC exactly 1/2. So if you believe the previous conjectures, then this is an implication. So 1/2 is the critical value for triangulations. And then you may ask, at 1/2, do you actually get also the conformal invariant limit? Do you get the CLE, the conformal invariant loop ensemble? And it may be the case, there was some discussion of Befora also on related subjects. Related to the conformal invariant limit, a simpler fact that we don't know how to prove is RSW estimates. This means that if you take a large rectangle and you look at the circles of your circle packing, which are in this rectangle, so you take only part of your circle packing, and you consider the percolation on these circles, then you have some uniform chance of obtaining a left-right crossing of the large rectangle at P equal 1/2. Russo-Simo-Welsh type estimates. So that's another conjecture, that at 1/2 you have such estimates. And indeed, Binyamini stated a very related conjecture. He discussed not circles, but squares. So he said, if you have a square that's packed with squares in such a way that, that it forms a triangulation, so no two squares touch at one, and no four squares touch at a point, then in 1/2 side percolation, you have some uniformly bounded chance for a left-right crossing. That is a conjecture of Binyamini. The results that I showed you imply this conjecture, but not at 1/2, but at some universal constant sufficiently close to 1. Okay, this is all I had to say. Thank you very much. If there is interest in the Lupo N model, I also prepared some slides on that. Thank you very much.